buffers, and we are going to see some basic concepts about normality, molality, and basically a little more about buffer, how it is prepared in the laboratory to create optimum conditions for a particular biochemical reaction to happen, or in general also when we were talking about protein separation, when we did the column chromatography part, we also saw the importance of buffers because proteins are very sensitive and they require an optimum pH. Now, who maintains the pH? It is the buffer that maintains the pH. So buffer is a solution that resist any change. Okay, so it's important because when you're separating the protein or the analyte of your interest, this buffer helps you to do that. And if you use a proper buffer, if you use a buffer which is optimum for that particular analyte, the separation is much better. Okay. Now, when we talk about column chromatography, we have seen the terms mobile phase, stationary phase, eluent. Okay, we have seen that, how to pack a column, how to equilibrate the matrix, all of that. So pH is an important factor. And why is the pH of a mobile phase so important? Because now we are discussing buffers. So yes, pH, it will change, it will resist the change in the pH. A buffer is a substance that resists change in the pH of the entire system. The pH of the mobile phase is adjusted to improve component separation and to extend the column life. So here the mobile phase, when you're going to load the protein or the analyte in a column, that protein or analyte is going to first interact with the matrix. It will either bind, if it is a size exclusion chromatography, the protein will enter inside, the smaller proteins will enter in the beads, the larger will escape through the void volume. Okay, but then after all of that, you have to continuously keep passing the mobile phase. Okay, that mobile phase is the buffer. That mobile phase will have a certain pH. That pH is going to help the analytes, help the protein to separate. So a proper pH by using a proper buffer is important because it improves the component separation, and it also is good in general for the life of the column. Otherwise, if you do not pass enough mobile phase, enough buffer through the column, then the column is going to get dry, it will crack, and obviously that column is not good, not desirable for a column chromatography. Now, how do we actually adjust the pH? So if I give you, say, just plain water, because water is an universal solvent, water is a base for many of the buffers, many of the reagents that we use. It can dissolve almost most of the things. Okay, most of the things can dissolve in water. So if I give you just plain water, and if I tell you to make it acidic, what would you do? You would simply add acid to it. So you will take HCl, that is hydrochloric acid, or you will take sulfuric acid and you add a few drops to it and the water becomes acidic. If I ask you to make it basic, then you will say, okay, ma'am, we can add, say, NaOH, we can add KOH, some base, some alkali to it, and then it will become basic. Okay, so you adjust the pH by introducing acid or by introducing base to this water, which is neutral or somewhere between 6.5 to 7, and then you can play around with the acidity or the basicity of the water. Okay, but the adjustment of pH is just not, should not just involve simply adding acid or alkali. So the pH adjustment is not only about adding acid or alkali, but the standard protocol or the standard practice is to make buffer solutions. And these buffer solutions can be preserved for a certain amount of time, for a certain duration of time, and they still remain stable. So that's what it offers. It offers stability. It offers the same results. If you use a particular buffer solution made by a standard, following a standard protocol, that buffer is going to give you the same results over and over. If you use the same buffer, say for 5 to 6 columns, definitely it will achieve what you are expecting it to achieve. So a good buffer will give you good separation of the analyte. It will give stability to the protein or to the biomolecule that you are looking after to separate. It will also ensure reproducibility. Okay, a good buffer should do that. But if your buffer solutions are not proper, if you're not using a buffer solution in the first place, if you're just adding some acid and some base to change the pH, then you will not obtain good separation of the analyte. You will not see any reproducibility. There will be no stability guaranteed to your analyte. Okay, so buffer solutions are very, very important, because if you don't use a proper buffer system, or if you're just randomly adding some acid and randomly adding some alkali, you may not achieve any separation, any reproducibility and stability. Okay, so how do you prepare the buffer? If you all have gone through the last recorded lecture that I have uploaded, in that I have actually emphasized on what is dissociation constant, what is association constant. So just go through it if you have not yet gone through it. A buffer solution is preferred. It's a combination, basically. It's not just dissolving one component in an aqueous system and then making a buffer. It's a combination. It's a combination of acid and base. Okay, so here you will use either a weak acid and a weak base. Okay, you may also use their salts, just like sodium salt. So sodium acetate is there, sodium carbonate is there, so you can use those salts also. So it's a combination of acid and its corresponding base conjugate. Okay, it is not strong, but it is weak acid or weak base. Common preparation, there are common preparations that include, like if you want to make a buffer, then what are the few preparations? Dripping an acid or alkali into an aqueous solution of salt while measuring the pH with a pH meter. So you know that now we are talking about pH, just like, I don't know whether you all have seen the instrument of pH meter, but just like spectrophotometer, you know, you absorb the wavelength, you see, look at the absorbance of the wave of the light that is passed through that analyte, and you can judge the functional group. You can at least estimate the functional group that is there. So that is one of the instruments that is used. Here we are using a pH meter. Now pH meter is not a very huge setup. It's a small, it is kept on the table. It has a probe, and you have to dip the probe in the liquid, and then you will see there is a digital display, and you will see the pH value of the substance in which you have dipped the pH probe. Okay, so now either while making a buffer, what you can do is you can take any salt. Okay, maybe you can say take sodium carbonate. You can take any salt, dissolve it in water, in an aqueous solution, dissolve it in an aqueous solution, and now there is a salt. If you want to make it an acidic buffer, then you can keep on adding acid drop wise to that suspension or to that solution, and stir it gently and check the pH. If now the pH has gone down, so because you're going to add acid, say you take dilute hydrochloric acid and you keep dropping in this sodium carbonate, then you might see that the pH is dropping. And if you want, say, a pH of 5, then you keep on adding HCl, stir it, dip the probe in that, and check in the display. If the pH is 5, stop it there itself. Okay, now that is for making it acidic. If you want to make a basic, or if you want to make an alkaline buffer, so what you do, you again do the same thing. You dissolve some salt into water, nicely dissolve it, make it a clear suspension. Now keep on adding a base or a base or an alkali. An alkali is something that is soluble in water. So you say NaOH. So you take NaOH and you drop NaOH drop wise in this sodium carbonate mix, and keep on checking the pH on the pH meter. It will reach, because it's a base, it is going to give you a pH of above 7. And if you are expecting that you want to work with a pH 9 buffer, wait until the display shows you 9, stir it always, and then when the display is 9, your buffer is ready. So this is not a very accurate way of making a buffer. Okay, it is just something like, if you're preparing, it's just like a recipe. If you're cooking something, you keep on tasting in between, and if you taste that salt is less, so you add salt to it. Okay, while making, if you taste something and if you say there's less spice into it, so you add some little spice. If there is less sugar, Like you are making a lemonade and you're tasting the lemonade and you feel that the lime juice is also less and the sugar is also less. So you add it later and you make a lemonade. So something like that. This is trial and error sort of thing. There is nothing standardized that you're following it. This is the first way of making. The second way, which is the most followed way, is that there are protocols. There are particular compositions that you have to take. So if you have a solution A and solution B, 5 ml of solution A and 35 ml of solution B, you have to mix them together and that will accurately give you a pH, say 7 buffer. 10 ml of solution A, 10 ml of solution B will give you, say, pH 8 buffer. So something like that. There are very standard tabulated protocols where you have to make the individual solutions and store them separately. So mixture A has to be made separately, mixture B has to be made separately, and then mix them in a certain quantity that will give you a respective pH. Okay, so just have to follow the table and you can make a buffer, and you have to just to confirm, measure the pH on a pH meter, and that will tell you whether the buffer of your interest is ready or not. Okay, now when you talk about buffers, there are two types of buffers. The first one is the acidic buffer and the second is the basic buffer or alkaline buffer. Now acidic buffers are used to maintain acidic pH, obviously. So if there are, see, many, not only neutral, everything, most of the reactions that happen in the human body, or if you're talking about a cell, okay, fine, neutral is the most preferred, but it also depends. Like if your source has been extracted or if your source has been isolated from an acidic environment, the cell will only function in an acidic environment. Whatever is being produced by the cell, it's a protein, it's a hormone, whatever it is, it's a metabolite. That metabolite, that protein will only be stable or active in acidic environment. So when you bring that isolated organism in the laboratory, you must make sure that you are also providing acidic environments to the particular cell. You are recreating the conditions. You're trying to make it more and more comfortable so that it gives you more and more yield of the protein. And at the same time, whatever it is giving you, it is stable also. So these sort of buffers are used depending upon what your source is. Is your source active at acidic pH, or is your source active at basic pH, or is your source active at neutral pH? Depends. Now, to maintain acidic environment, you use acidic buffers. It has acidic pH somewhere between, say, 1 to 6, 1 to 6.5, close to neutrality. Okay, prepared by mixing a weak acid and its salt with a strong base. So here you have a weak acid and a strong base. Okay, pH of these solutions are always below 7. These solutions consist of weak acid and a salt of weak acid. Okay, so actually weak acid, a salt of weak acid, and with a strong base. This sentence is incomplete. Now the example of acidic buffer is the solution of an acetic acid and sodium acetate. So acetic acid is an acid, okay? It's a weak acid. Now, why do I call it as a weak acid? It is a weak acid because acetic acid undergoes incomplete dissociation. So when you add, for example, when you add HCl to water, so what will happen? There is a dissociation, H plus and Cl minus. So HCl completely dissociates into H plus and Cl minus. So this is a strong acid. But when you add acetic acid to water, complete dissociation is not seen. Okay, they partially, some of them dissociate, some of the acetic acid molecules do not dissociate. So that makes it a weak acid. Now you're using a weak acid and you're using sodium acetate. So it is a salt of weak acid. Acetate. Acetate is weak. Okay. So it is a salt of weak acid. So when you mix acetic acid, it's a weak acid, plus a salt of weak acid, you get a buffer and the pH is 4.74. Okay. Now they are in equal concentration. So acetic acid is also in the same concentration as sodium acetate. So when you mix these two components, you can say that one is A and one is B. When I was earlier explaining, I said no, A and B. So what you do, you make two separate solutions. of acetic acid solution A and of sodium acetate solution B, and then you mix them. And when you mix them, in that mixing also has to be in equal amount, because you're talking about equal concentration. So the concentration, the amount of acetic acid in water, the amount of sodium acetate in water also has to be same. And then there is a certain proportion where you mix them together, and when you check the pH, you see that the pH is in the acidic side. So we make acidic buffers like this. There are many other acidic buffers also. This is just one example of the acidic buffer. Now we talk about alkaline buffer. Again, these are used to maintain the basic conditions. So basically, see, there are a lot of proteins which are alkaline proteins. Okay, alkaline proteins are active at alkaline pH. When the pH drops down, they are not active. For example, in the digestive system, we know that there is something which is trypsin. Okay, when the food enters into the small intestine, there is bile juice that comes for the further step of digestion. And then there is trypsin. Trypsin is only active at alkaline pH. So when you are working with trypsin, especially the digestive system, trypsin from the digestive system, then you have to maintain basic conditions. So in such cases, then if you are doing something in the laboratory, you'll have to recreate those conditions and provide basic conditions for the further study. Now, basic buffer has a basic pH, and it is prepared by mixing a weak base. So for acidic buffer, it was weak acid. For basic buffer, it is weak base. Okay, and the salt with strong acid. So again, we are going to use a weak base and its salt here. Okay, the pH of these solutions are above 7. So when you're talking about alkaline pH, it is above 7. They contain a weak base and a salt of weak base. For example, alkaline buffer solution is a mixture of ammonium hydroxide and ammonium chloride. So see, ammonium hydroxide and ammonium chloride. This is a weak base. Again, if you talk about a strong base, NaOH, let us take NaOH. When you add to water, it simply dissociates into Na plus and OH minus. So the dissociation here is 100%. So that's why it becomes a strong base or a strong alkali. But water soluble bases are called as alkali. I hope you all know this, right? Correct? Everybody knows that. So NaOH is water soluble, and that's why we call it as a base or as an alkali also. So Na plus OH minus. But here when you add ammonium hydroxide to water, it will not give complete dissociation. It will undergo incomplete or partial dissociation. It does not ionize completely in water. So that's why it becomes a weak base. And the salt of ammonium, the salt here is ammonium chloride. So when you mix both of them, they give you a pH 9.25 buffer. So again, see, if you see this is A and this is B, you're going to make two separate solutions and you are going to mix them together, or you weigh whatever is the amount that is required and mix them in the same container. Even that is also okay. So this is like, this is a mechanism of buffering action. Again, here there is acetic acid and sodium acetate. So acidic buffer actually we are talking about. So the salt is completely ionized and the weak acid is partially ionized. So you look at this component, it is acetic sodium acetate. It is a salt of weak salt. It's a weak, basically weak acid salt. And this is acetic acid. So when you add sodium acetate, it will completely ionize into sodium plus acetate. Okay, so Na plus and CH3COO minus. Some of them again come together and make sodium acetate. That's why this sign is used here as a reversible. It's a reversible reaction again. Now, when you add acetic acid, it will also dissociate into H plus and CH3COO minus, but this is partly dissociated. So partly ionization happens in acetic acid. That's why it is also called as a weak acid. Okay. Now, on addition of acid, the released protons of acid will be removed by the acetate ions to form acidic acid molecule. So if this is what you get, H plus and CH3COO minus. Now, if you're going to add acid to this, okay, so the H plus will again combine and it will again form acetic acid. On addition of a base, what will happen? The hydroxide that is released. So when you add acid to this particular suspension or solution, so H plus dissociates, right? That ionized H plus will go and combine with CH3COO minus and it will again form CH3COOH. But if you add base, then what happens? Base is what? Basically OH minus. Whatever hydroxide ions are released by the base. Okay, so if you're adding, say, NaOH, so NaOH will give you OH minus. This is the hydroxide ion. This will go and combine with the H plus and it will form H2O from the buffer solution. So this is how the buffering action is. Now, preparation of a buffer solution is again by mixing two different, you have a weak acid and you have a salt of the weak acid, or you have a weak base, you have a salt of the weak base. Then for acid, there is always a conjugate base. So you have to mix the weak bases with their corresponding conjugate acids, or you have to mix the weak acids with the corresponding conjugate bases. And when you mix them, then you get a buffering system. For example, now phosphate buffer. So phosphate buffer is very commonly used buffer. Why? Because it is at the neutral pH, and this is most of the biomolecules, they are stable at a neutral pH. So phosphate buffer is very commonly, very routinely made in the laboratories. So here, what are the mixtures? So there are these two mixtures that you use. So there can be, say, sodium phosphate buffer, or you can also use potassium phosphate buffer. So potassium phosphate buffer is very, very commonly used in the biochemistry labs. So basically what you do here is, if you're talking about potassium phosphate, then there is K2HPO4 and then there is KH2PO4. Okay, dipotassium hydrogen phosphate, potassium dihydrogen phosphate. Okay, so here there is H2PO4. So this is like acidic, this is like basic in nature. Okay, so you're going to make a suspension solution of this, you're going to make a solution of this and then mix them together. Okay, so I will make a separate solution of, say, potassium dihydrogen phosphate. I'll make a separate solution of dipotassium hydrogen phosphate. Okay, I'll keep them separately. Now when I want to make a phosphate buffer, mostly I take about 19.5 ml of this, okay, and if I'm not wrong, 30.5 ml of this, something like this. And when I add them together, I get 50 ml. Now this 50 ml, I will level it up to 100 ml using water. Okay, so in a measuring cylinder, I first take 19.5 ml of solution A, then I add 30.5 ml of solution B, and then it should come up to 50 ml. And when it comes to 50 ml, I level it up to 100 ml, and now my buffer is ready to use. If I check the pH, then the pH is 7.4 at that concentration. Okay, so there is a table basically of phosphate buffer which is available on the internet. Also there are books, also there are manuals, laboratory manuals of buffers. So there they will have the composition of all the buffers. So if you want to make phosphate buffer, if you want to make, say, particularly potassium phosphate buffer, because some of the cells are very specific about not having sodium. Okay, some systems, sometimes some reactions do not want sodium, so we can eliminate sodium, but we want a phosphate buffer because the pH is neutral. So at that time we can use potassium phosphate buffer. So this is the composition. So if you want to make of a particular concentration, so then you can mix like this and you have to check the pH. The pH will come to 77.4 because these are all standardized things. Okay, they are all tried and tested. They are just not randomly mentioned like that. Now, when we talk about buffer, there is one thing is buffering capacity. Okay, this was all covered in the last class, which is the recorded lecture, which is available. I have shared the link. So if you go through it, you will get to know what I am right now addressing. More the concentration, more is the buffering capacity. Now the word concentration is very, very important. Okay, when we are talking about buffers, concentration is very important, because now you will understand that, okay, I'm mixing solution A, solution B together, but what normality is each solution? What molarity is each solution? Now we are coming to concentration. So what is concentration? How we know that a solution is made up of solute and a solvent. Okay, so solute, out of which solute may be in lesser amounts. Okay, solvent is in higher amount. Okay, so solute plus solvent, okay, that gives you a solution. This is something that you all have already covered in class 9th, 11th, 12th. So this is more of a revision here. So maybe this is less, this is more, and then when you mix them together, you get a solution. Now I say, see, if I have two containers and then I take, say, water into it, and both of them have same amount of water, which is 1 liter of water. So now if I'm adding, say, 10 gram of NaCl in this, and I'm adding 20 gram of NaCl in this container, say container A and container B, and I dissolve them. So out of which of the container will have a higher concentration? Obviously container B. B will be of a higher concentration than A. Why? Because in container B, I added more NaCl as compared to container A. But when you are talking in, say, in chemistry, when you are going to express this, just merely saying that container B is more concentrated than container A does not make any sense. You need a certain number to express that how concentrated it is. Okay, because I'm using a more concentrated solution, I'm using a less concentrated solution, I'm using a medium concentrated solution is not going to give you any understanding. So you need to express them, and when you express them, you need some terms like normality, molarity, molality, parts per million. Okay, so these are some terms that we will see today. Now concentration, as I said, we will just look at the concept of molarity now. So when you talk about molarity, what is molarity? As per the definition of molarity, it is number of moles of a solute. Because we are talking, see, when we are talking about making a solution, there will always be a solute and there will always be a solvent. Okay, so number of moles of a solute in 1 liter of solution. So here your volume is definite here. It is 1 liter. Okay, here now it is always denoted by a capital M. Molarity is always denoted as a capital M. Okay, I will make the arrow like this so it's easy to understand. So if you write it in a formula, you will see it is number of solute divided by volume of solution. Okay. So now, for example, we are going to make, say, 5 molar of hydrochloric acid. So what will I do? If I want to take, if I want to make 5 molar of HCl is equal to 5 moles of HCl plus, I have to add this now to 1 liter of water. And then I get a 5 molar HCl solution. So number of moles of solute. Okay, that is important. So number of moles of solute in 1 liter of solution or in 1 liter of my solvent. and both of them will give me a solution. Now this solution is 5 molar. If I want to make 6 molar, then I add 6 moles of HCl in 1 liter of solution. If I have say 10 molar solution of HCl, then it means that 10 moles in 1 liter. Okay, so this is basically molar solution. Now there is something which is also molality. Okay, now what is molality? Molality is generally represented as small m, always. Molarity is capital M, molality is small l. So here number of moles of solute in 1 kg of solvent. See, when we were talking about molarity, it was 1 liter of solvent. Here it is 1 kg of solvent. So solvent is considered here. Okay, so here if you see the small m is equal to, if you write down the formula, number of moles of solute divided by mass of solvent. So if I want to make a 5 molar solution, okay, initially I made a 5 molar solution, but if now I want to make a 5 molar solution, then what do? I take, first I'll write small m because it is 5 molar. Okay, 5 molar solution of HCl. So what will I do now? I will take 5 moles of HCl plus 1 kg of the solvent. That solvent can be water, depends on what system you are working. If you are working with aqueous HCl solution, then you will use water there. So 1 kg of your solvent, and this will give you a 5 molar HCl solution. Now if you're making a 10 molar HCl solution, so nothing but 10 moles plus 1 kg of solvent. Okay, now in this case again, if you want to see, this is 1 liter, so you can also make it converted into terms of ml. The formula, how would you do that? So molarity is equal to mass of solute, okay, into divided by, first we'll say volume of solution, and if you want to convert it into say ml, then you just have to multiply with 1000. So it will be converted into milliliters. Same happens here also, because here you are going to take 1 kg. So if you want to convert it into say grams, you will be dividing it. So division karenge, so it will go up. So it will become 1000, and then it will be expressed in grams also. Okay. So now if we'll just discuss one example here, a numerical. Calculate molarity of 500 gram of NaOH in water, and the volume has to be to have a solution of 5 liters. Okay, so this is going to be the volume. Now you know that the volume is 5 liter. What is given is the volume is 5 liter, and you know that the mass of the solute is 500 gram here, 500 grams of NaOH. Okay, what is the molecular mass of NaOH?
40.
40. How do you calculate the molecular mass? Molecular mass of sodium plus molecular mass of oxygen plus molecular mass of hydrogen. So that is 23 plus 16 plus 1, it will give you 40. So the molecular mass of NaOH is 40. Now the molarity is, the formula of molarity is, say, mass of solute divided by molecular mass of that particular solute multiplied by the volume. Okay, so how much is the mass of solute given in the numerical? It is 500. Divided by what is the molecular mass? 40. How much is the volume? 5. So you will have 500 divided by 20 by 200. Is it correct? Yes. So this solution that you're going to make will be of 2.5 molar. The concentration you can call, or you can also call it as the strength. So this is what is the importance of concentration. Now, if I go back and if I tell that, okay, this was 5 molar and this is 10 molar. So now I have a definite concentration. I have a definite number that is going to tell me that solution B is more concentrated than solution A. How much more concentration? It is double the concentration of solution A. What is the concentration? This is 10 molar, this is 5 molar. Okay, so that is the reason why you need to express the concentration. You need some certain terms, you need to calculate them, you need to find the normality, molarity, molality, all of these. So why this is important in buffer also, because we are going to make, say, one normal buffer, we are going to make 0.1 normal buffer, or we are going to make 1 molar buffer, or we are going to make molar buffer. Okay, so all of these concentrations are going to play an important role depending upon how much strength of buffer we require for a particular column, for a particular analyte to come out. Because suppose now you're doing say ion exchange chromatography. Okay, ion exchange chromatography mein ion ke exchange ki wajah se your analyte is going to bind to, say, the matrix. Now you saw, so you are trying a column and you are actually doing a trial and error method. So what do you do now? First you equilibrate. What are the steps? I think there was, this question was there in your exam also. So what do you do first? Equilibrate. Equilibrate the matrix with buffer. Okay, now suppose here you are using a 0.5, okay, 0.05 molar phosphate buffer. You are using this buffer here for equilibration. After that, after you equilibrate, you degas. After the degassing, you pack the column. Okay, after packing the column, you always maintain the level of buffer over the bed of the matrix, because you don't want the column to get dry. So pack the column properly. Now you have to load your sample, load the protein mix. It's a mixture of lot of other things. After you do that, allow the protein to pass through the column. Now that binding, during the binding process also, you will have to add the buffer. Keep on adding buffer. Okay, so which buffer you are going to use? Suppose binding ke liye bhi you realize that 0.05 molar buffer is only suitable. So when I add this buffer, the pH is optimum and my protein of interest is binding to the, say, matrix. After the binding procedure is over, now you have to elute. Okay, so say suppose load the buffer, bind the protein mix. Okay, now what is the next thing? You have to elute. Now after you start the elution procedure, you realized that, okay, I am going to pass, say, 0.05 molar of buffer through the column, and I'm going to collect the filtrate, or I'm going to collect the eluent. The right word is collection of eluent. Collection of eluent. So you're going to collect the eluent. After you collect the eluent, what will you do? Either you do a UV visible spectroscopy here, or you do an assay, enzyme assay. Okay, these two things will tell you whether there is the protein in the eluent or not. If protein is in the eluent or not. Okay, you collected so many eluent tubes. Say you collected about 20 eluent tubes, and you still did not see any protein in that eluent. So what does it mean? You might want to increase the strength of the buffer. So this is the point not 5. Point not 5 you use for equilibration. Point not 5 you used for binding. Now for elution, point not 5 may not work. So then what you do? You increase the strength. You increase the strength, say, to 0.1 molar. You double the strength now. And when you pass this 0.1 molar buffer through your column, then you start again collecting the eluent in the test tubes. When you assay, you will see the assay is positive. So it means that increasing the strength of the buffer, the protein came out of the column. So this is the role of pH changing. Okay, this is the role of pH changing that may help you to elute your protein, which has been bound tightly to the matrix. Sometimes just using a buffer is not enough. You might have to add some extra salt to it. So salt, you add salt to the buffer and then you pass that buffer, then you will see that the protein is coming out, because that is helping the protein and the interaction between the matrix to weaken. So they become weak and then it loses the protein and the protein comes out in the eluent. So in the eluent step, the elution step, in the binding step, everywhere the strength of the buffer plays a very, very important role. And that is why we are now looking at how to express them in terms of molar solutions, in terms of normal, in terms of molal. So we saw what is molal also, we saw what is normal also, molar also. Now we are going to move to normality. Do you know the definition of normality? You all have already done this. Whatever we are doing today is revision. Do you know the definition of one normal solution? Anybody? Do you want to write it in the chat box? Okay, so when we talk about reactions in chemistry, we always say, for example, we have this reaction, H2SO4 plus, say, NaOH. What will it give? When you react H2SO4 with NaOH, what will it give? Any idea? Okay, and we will have to balance it. So we balance it. Okay, so you have H2SO4 reacting with 2 NaOH and it will give you sodium sulfate and it will give you water. Now, if you see in terms of moles, okay, when we are talking about number of gram equivalents in one. Yes, Ajinkya, very correct. Number of gram equivalents dissolved in 1 liter of solution will give you one normal solution. Okay, so correct. Now, if you see at this concept here, I'm just going to revise some things. So you'll have 1 mole of H2SO4, 2 moles of NaOH. Okay, so if you look at the reactants now, the number of moles are different. Okay, now this is 1, this is 2. For another example, say H2 plus N2 will give you, it's a reversible reaction. It is going to give you ammonia. Okay, it requires a catalyst also. It's not so easy. It's not a very easy reaction. So now if you try to balance it, then say, okay, so if you now look at this, this is 3 moles, this is 1 mole. Okay, and how many moles of product you got? You got 2 moles of product here. Okay, now here you will see that the number of moles are not same when you talk about the reactants. So unless and until you balance the reaction, unless and until I added these coefficients here, okay, I was not able to tell how many moles are required for this particular reaction to happen. Okay, so balancing of chemical reaction is important, because in the nature we are following the law of conservation of mass. We see the reactions happening in the nature which follow the law of conservation of mass, and hence we balance it and we get the we follow the same law here also. So the number of reactants or the mass of the reactants is equal to the mass of the product. But unless and until I balance it, I cannot comment upon how many moles participated in this particular reaction to give me that much of product. So hence what happens is we need something more that will tell us the exact value of the reactants that are interacting and reacting and giving us a product. So how about expressing, say, in terms of grams? How about 1 gram of H2SO4 reacts with 1 gram of NaOH? Okay, this gram is now giving me a certain value. Okay, so how about 1 gram of hydrogen reacting with 1 gram of nitrogen? Okay, so when I get these kind of fixed values, then I omit the confusion. I omit the confusion that the moles get into. Okay, so in any chemical reaction, number of gram equivalent of reactants will always be equal. So every time you look at any chemical reaction, if you look at in terms of gram equivalent, you will see that number of gram equivalents of a reactant is always equal. Okay. Now, how to calculate an equivalent mass? Why am I after the equivalent mass? I am after the equivalent mass because as per the definition of normality, the definition of normality says that the number of gram equivalents of a solute present in 1 liter of a solution. So if I want to make a one normal solution, if I want to make a one normal solution of NaOH, so it means that gram equivalent weight of NaOH divided by the volume. Okay, so this gram equivalent weight is very, very important. That's why we are going back to the basics that you did in 11th and 12th. Now, how do you calculate the equivalent? Does anybody know how to calculate the equivalent weight? How to calculate the equivalent weight, or we'll use the word mass. This is a bit of chemistry, but how to calculate it is equal to molecular weight divided by the valence factor. Okay, equivalent mass can be calculated by this formula. Now, if you take an example of HCl, okay, what you'll do is molecular weight of HCl divided by the valency factor. Now, this is an acid. So the valency here is going to be the, say, basicity. So when you, how many H plus are there? There's only one H plus. So the valency of HCl becomes 1. So molecular weight divided by 1 is going to give you the equivalent mass of HCl. What is the equivalent mass of HCl? What is hydrogen ka mass? What is chlorine's mass?
35.5.
37.5 or 35.5? Hello, what is the mass of chlorine?
35.5.
35.5. So divided by 1, that is the valency. Okay, so whatever you are going to get is 36.5. This is going to be the equivalent mass of hydrogen. Okay, now if you say, if I take a base NaOH, how will I calculate the equivalent mass of NaOH? Molecular weight or molecular mass divided by valency. So if it is an acid, then the valency factor is based on the basicity. If it is a base, then the valency factor is based on the acidity. So here, if I add it to water, or if I see how many OH is it going to give, so it is only going to give 1 OH. So it means that the valency is 1. What is the molecular mass? 40 divided by 1. So here equivalent weight of NaOH is 40 only. Okay. If it was, say, calcium hydroxide, So how many OHs are there? 2. So the valency factor becomes 2. So if I want to calculate the equivalent mass of calcium hydroxide, then what will I do? I'll take the molecular mass divided by 2. Okay, is this understood? Okay, similarly, if it is H2SO4, if it is H2SO4 and if I want to calculate the equivalent mass of H2SO4, there are 2 H. So the valency is 2 here. So H2SO4 becomes molecular mass of H2SO4 divided by 2. Okay, so here it is 1 plus 32 plus 16 fours are 64. So 33, so probably it will be 97 if I'm not wrong. So 97 divided by 2 and that can give me 4, 8 is
80.5.
0.5. So this is going to be the equivalent mass of sulfuric acid. Okay. Now, is it always dependent on the number of H and the number of OH? Is the valency always related to H and OH? Sometimes we also have to go in the structure of the particular acid. For example, again, phosphoric acid. So if you look at, say, a phosphoric acid, it's a weak acid, and the formula of phosphoric acid is H3PO4. Okay. Now, if you look at, say, different structures, so this is H3PO4, this is H3PO3, and this is H3PO2. If you look at hydrogen, you'll say that there are 3 hydrogens here. So it means that the valency is always 3. But it does not happen like that, because if you look at the structure, you will see okay, so here there will be one hydrogen, 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 and then hydrogen, and here it will be hydrogen, and here it will be hydrogen, and there will be one more hydrogen here which will be bound to this. Okay, now it means this will break, this will break, this will break. So you will say that the valency here could be 3, but here this can easily break, this can easily break, but the valency here will be 2. Here the valency will be 1. So depending upon the structure also the valency is determined. It is not always a thumb rule that the number of hydrogens will give you the valency or the number of OH will give you the valency. It is also the structure that will determine that whether it will give away, whether the valency is 3, whether the valency is 2, whether the valency is 1, or whatever is the valency, the structure is also going to determine that. Okay. Now, calcium hydroxide, I think we discussed about it, right? So when it comes to salt, so we saw about acid, we saw about base. Let us consider salt now. What is a salt? When you mix acid and base, you get a salt, correct? So you get NaCl plus H2, right? So this is the acid and base will react and give you a salt. So when you have a salt now, how do you calculate the equivalent mass of the salt? Here you are going to consider, so valency factor here is going to be the total positive or negative charges. Okay, because what is a salt? A salt is Na plus and Cl minus. So you will have a cation, you will have an anion also. So there will be positive and negative charges. You have to take the total positive or the negative charges on, say, cation, anion. Okay, so that is what you are going to consider. So equivalent mass of a salt is equal to molecular weight divided by this valency. How many positive or negative charges are there and how many cations and anions are there. Now, for example, if you have a salt which is sodium carbonate. Okay, so how many, if I, at a time I can only choose one. If I'm deciding to choose cation, so let me only take cation. So here, how many cations are there? 2 cations are there. So the valency is 2. Okay, now the molecular, how will I calculate the equivalent mass? The equivalent mass is going to be molecular weight divided by 2. Okay, now if I have aluminium chloride, molecular weight divided by valency. So how many how many charges are there on this cation on aluminium? How many charges are there?
3.
3 charges. Okay, how many aluminium, how much of aluminium is there? Only 1, right? So 3 into 1, just 3. What is the molecular weight? Whatever is the molecular weight, you put that molecular weight here and you will get the equivalent mass of aluminium chloride. Okay, now if I have something which is aluminium sulfate, okay, if I have aluminium sulfate, then I have here 2 aluminium, okay, 2 aluminium, and that has 3 charges. So 2 into 3 becomes 6. So this is the valency. What I have done, I have taken the product of number of cations. How many number of cations are there? 2 number of cations are there, multiplied by the charges on the cation. So number of cation multiplied by charges on cation. That is the valency factor. And then what I will do, I will take the molecular weight of aluminium sulfate divided by 6. And whatever equivalent mass I will get is, whatever value I get is the equivalent mass of aluminium sulfate. Okay. Is this clear?
Yes, ma'am.
Okay. So number of gram equivalent is equal to mass divided by equivalent weight. This is the formula. Now, there is one question that I'll ask you here is, number of gram equivalent present is 0.8 gram of NaOH. Okay, so, okay, not this one. No. Okay, find the number of gram equivalent. Present in 0.8 gram of NaOH. So what will you do here? Now you will have the formula, number of gram equivalent is equal to mass divided by equivalent weight. Equivalent weight, how to determine equivalent weight? We just saw molecular weight divided by valency. So what is the molecular weight of NaOH? 40 divided by 1 is equal to 40. So you have 40 as the equivalent weight. Okay. Now, so you just substitute that in the formula. The mass given is 0.8 divided by 40. So you will say 8 by 400, which is equal to, it comes to 0.02. Is this correct? So the number of gram equivalent weight is 0.02 grams. Okay, so this is the way you will calculate. So why is this important? Because one normal solution is number of gram equivalent divided by 1000. If you're going to do 1 liter of solution, if you're going to do ml, then you are going to divide it by 1000 further. Okay, so this is all about gram equivalent. Now we go to normality. So normality, the definition of normality is number of gram or mole equivalents of solute, which is present in 1 liter of solution. Now we studied what is normality, what is molarity, and what is molality. All of these three terms are going to be extremely important when you make buffers. Especially normality is very, very important when you make buffers, because most of the time what you are going to do is you are going to use a solute, you're going to dissolve it in the water or an aqueous base.